Hello everybody. I've decided I'd do a short little video here for you on the addition rule for probability. There seems to be a lot of questions that have arisen from this section. And I grant you that we have entered the part of probability that is by far the most challenging. And that is the idea of compound probabilities using the words and or the word or. So today's lesson is going to cover the word or. Before we can do that, we need to first kind of take a look at a probability table. So I've collected data here on endangered species. You can see there's 4 different categories of endangered species, and I have them broken into 2 different places, here in the US and the rest of the world. And I've taken each of them and totaled them up. So the grand total number of endangered species is 668. And I've got a total here for each of our US and for the foreign as well. So simple probability. Simple probability would ask a question like, well, what's the probability that the endangered species is a mammal? And we know that probability is always the number of desired outcomes divided by the total number of outcomes. So since I'm looking at mammals, I want to look at what's the total number of mammals that are endangered. And following this across are 68 in the US, 251 foreign, so 319 total. So our probability would be 319 out of the grand total of endangered species, which in this case is 668. Very simple probability. If I was to look at, okay, what's the probability that the endangered species is here in America, in the United States? Well, I need again find the total number for the United States, 170. And divide that by the total, 668. Okay. Simple probability. Where probability gets a little more challenging, a little more complex, and I think this is what's confusing a lot of you, is when it starts to become situations where they're looking for more than one possible outcome. So in these situations, we're gonna run into a concept called mutually exclusive. And the term mutually exclusive simply means that the 2 objects do not overlap or cannot occur at the same time. So, do not overlap or cannot occur at the same time. Sorry about that getting a little fuzzy. So if I was to ask a question like, what's the probability that the endangered species was a bird or an amphibian? I think you would agree that from your science classes, biology or a previous science course, that birds cannot be amphibians and amphibians cannot be birds. That means that if something is found in this line of birds, it cannot also be found in this line of amphibians and vice versa. So these 2 groups are known as being mutually exclusive. They cannot occur at the same time. They cannot be both a bird and an amphibian at the same time. Something cannot be in the US at the same time that it is in the rest of the world. So being in the US and being in the rest of the world, these categories are mutually exclusive. So as we're addressing the idea of mutually exclusive concepts, we're really starting to look at the word or. And the word or is going to imply we're going to use addition to solve these problems. So what you need to be asking yourself first and foremost is, are the objects mutually exclusive? Because if they are mutually exclusive, then it's a simple addition problem. So birds or amphibians. And I think I addressed this one. It cannot be a bird while as an amphibian. So I want to go and see, okay, what's the probability that it's a bird or an amphibian? Well, logic would state that I want to look at how many things are birds, how many things are amphibians. If I add those 2 up, I can get the total number of species that are birds or amphibians, and I can find my probability. So our probability in this case is going to be probability of it being a bird, 252 out of 668. Probability of it being an amphibian, 19 out of 668. So the grand probability here is, oh boy, a little quick math, 271 out of 668. They were mutually exclusive. All I had to do was add together the total number for each. And you might be saying, well, I can do that without doing all that fractional addition, and you are right, you can. So if I was looking at birds or reptiles, I'd skip down here. I'd say, okay, birds, is it mutually exclusive? Absolutely. I can't be a bird at the same time I'm a reptile. So I just need to take my birds plus my reptiles, add them together. So 252 plus 78, 10, carry a 1, 13, carry a 1, 330. So my probability of it being a bird or a reptile would be 330 out of 668. All right, now the more challenging part of this. You know, this is kind of interesting, but it gets even more interesting if the objects are not mutually exclusive. So, before I go there, what he introduces in the video is that you can do a quick little equation for this, saying that the probability of A plus the probability of B is equal to the probability of A or B if they are mutually exclusive. Simply add together the probability of each of these things. Probability of a bird, 252 out of 668. Probability of amphibian, 19 out of 668. Just add the two of them together. Remember, when you add together fractions, you keep the denominator and simply add together the numerator. All right, now back to what I was saying. And the dog just took off after the cat. What if they are not mutually exclusive? All right, so what if there is something that is in common? What if they do overlap? And an example of this would be, what is the probability of it being a reptile or it being something that's in the United States? Well, if I go back and look at my table real quick, the probability of being a reptile is 78 total reptiles. So the probability of being a reptile is 78 out of 668. Easy enough. The probability of it being in the United States. Well, the probability of it being in the United States, there are 170 endangered species in the United States. There are 668 total. So if I do the probability, it's 170 out of 668. But the problem is that when I went about doing that, there was overlap. When I went across this column, let me grab a different color pen here real quick. When I went across the column, I was counting 14 in the United States, 64 foreign, for a total of 78. When I looked at it at the United States, I was counting the 68 that were mammals, 77 that were birds, 14 that were amphibians, and reptiles, and 11 that were amphibians. What happened? Well, what happened is, if you look right here, those 14 reptiles got counted twice. They got counted once when I went across and tallied up the total number of reptiles, and they got counted a second time when I counted down through here and counted up the total number for the United States. They are my overlap. An overlap occurs when you've counted them in both directions. See, when they were mutually exclusive, we were just going across the row and there was no overlap. But in this case, there's a crossing of my two data sets. They're intersecting at some spot. The intersection's right here. So that number's being counted twice. So what I need to do when I do my probability, get back to my page, I need to look at, okay, what's the probability that it was a reptile? Well, there were 78. plus what's the probability it was from the United States. But if I just do that, I have left those 14 in there because remember, they were counted in this one. They were counted again in this one. So I've overcounted by 14. So what I do is I subtract back off the overlap. All right, a little quick math here. 248 minus 14 would be 238, 234. So 234 out of 668. Okay, let's jump real quickly. I don't want to take a whole lot more time. I'm already up to 10 minutes, I see. But we're going to jump here onto the laptop. And here's the worksheet that they gave you in Khan to practice this concept. So again, I've got a probability table here. If I scroll down, let's see what the first question is. Okay, simple probability question. Find the probability of someone preferring a dog. So I'll go up here, prefers dog. Well, 56 people. 56 people in this survey preferred a dog. I didn't really read it real quick, but I'm guessing they asked, I did read it. I did all these problems before I got on. So they asked, did you prefer a dog? Did you prefer a cat? Or did you have no preference? So my probability would be 56. My grand total people surveyed was 100. I can check that. Bingo, bango, bongo, onward we go. All right, in this sample of are the events preferring dogs and preferring cats mutually exclusive? So preferring dogs, that goes horizontally straight across. Preferring cats, that goes horizontally straight across. There's no overlap. They're not intersecting. They are parallel to each other in the table. So yes, these are for certain mutually exclusive. It says find the probability that someone prefers a cat or a dog. So since they are mutually exclusive, always the first question I ask myself, are they mutually exclusive? I can just go over here. I can add up the 56 that prefer dogs to the 36 that prefer cats. That's 92. So my answer to the third question should be 92 out of 100. Are the events prefers dogs and female mutually exclusive? Okay, back up to my table for a minute. So I can see that when I come across here and then I come down here, that my two lines have intersected. They've overlapped. They've overlapped on these 20 females. These 20 females preferred dogs, and these 20 females were just that, females. So because there was overlap, these are not mutually exclusive. So how am I going to do their probability? Well, I'm going to look at what's the probability of it being a dog, what's the probability of it being a cat, and then I'm going to subtract off that overlap. Or, I'm sorry, not a cat, a female. So the probability of it being a dog was 56. The probability of it being a female was 52. So I'm going to add those together. The word was or that was in the problem. 56 plus 52 is 108. But again, I've counted these 20 people right here twice. They were counted in the column for females. They were counted in the row for dogs. So I'm going to take those 20 back off. 108 minus 20 is 88. So my probability here should be 88 out of 100. Ooh, too far. I did read some of the comments at the bottom, and it does do a little bit of clarification if you do have some additional questions on this. Okay, so we went 5 for 5 here. When you get into the problems that it gives you on the next page, I really, really, really suggest you take a moment and you make yourself up a little table like this, because the table will really help you see, I believe, if there's going to be overlap or not. Do you have things that are going horizontally in both cases, in which case there's no overlap, or vertically in both cases? I could say, what's the probability that someone was a male or a female? Well, those don't overlap. You can't be a male the same time you're a female. So add these two together, there's 100. 100 out of 100. There's a 100% chance we pick somebody that was male or female. Or is the problem one that's going to be not mutually exclusive, where it's going to come across? What's the probability of someone prefers a cat, or they are a male? In which case, because it was crossing, there is overlap. These 10 people right here would be counted twice, and I need to subtract them back off at the end. All right, that mini little lesson went a little longer than I'd hoped, but hopefully that helps explain this a little bit better for you. I know this is challenging, this section. Please, if you have questions, if you run into a problem and you have a question on the problem, screenshot it real quick, shoot me an email. I'll do my best to do an explanation of it for you, and I'll send it back to you kind of as quick as I can. So, hey, everybody, take care. Hope you're doing well, and be safe. May is here, so the countdown is on. Only 27 more days left in this 9 weeks. So keep going strong, everyone.